Good morning, class. We are continuing with our lectures. This is section 1.2 of chapter 1, Mathematical Models, Catalog of Essential Functions. Okay. We covered 4 ways to represent a function, and now we're going to move on. So what we did, 4 ways representation, verbally, numerically, visually, algebraically, all of them were discussed. A function is considered to be an even function if f of minus x is minus f of x is equal to f of x. My apologies. When you replace the x with minus x, nothing happens, which means it is symmetric. The graph is symmetric with respect to the y-axis. The y-axis. And we have the odd function where you replace the x with minus x and you get minus f of x, which means odd symmetry, which means symmetric with respect to the origin. We see a function machine, x goes in, f of x comes out, okay? And in short, a function is a set of pairs in essence, okay? However you put that, whether you put it through the formula graph or a set builder, such that the first coordinate cannot repeat, and that's why we can use the vertical line test to look at the graph. A graph fails a vertical line test, it won't be a function. And then we have an increasing and decreasing. A function is considered increasing. As we go from left to right, obviously x increases. What happens to the y? If the y increases also, that is considered an increasing function. Otherwise, it's a decreasing function. Okay, so let's move on from here and go to the new stuff. Again, I want to make sure everybody is muted as you come in. Make sure your audio video is muted. So with that being the case, let's start the new topic. And by the way, class, the new topic is going to go fairly fast, and it's honestly fairly boring because you've seen it, there's nothing much here. So maybe, you know, in some cases, I ask you to help me read this. Could somebody read this paragraph for us? Because again, I'm sure you're tired of hearing my voice. Could somebody read this paragraph, please?
I'll read it.
Please.
A mathematical model is a mathematical description, often by means of a function or an equation, of a real-world phenomenon. The purpose of the model is to understand the phenomenon and perhaps to make predictions about future behavior. A mathematical model is never a completely accurate representation of a physical situation. It is an idealization.
Fantastic. Thank you so much, Joseph. So the bottom line is, there is a reason for study of mathematics, because a lot of stuff can be explained by math, and in many cases when we make up equations, it makes it a lot easier to understand, follow, and even solve questions that they seem to be impossible. Now, there are many types of functions we have seen in pre-calculus. For example, the linear function y or f of x equals mx plus b. A polynomial function, p of x is a sub n x to the power of n, and it continues all the way to a sub 0. Then we have power functions, which is x to the power of a. We have rational functions, and also trigonometric functions, exponential functions, logarithmic functions, and finally, algebraic functions, something that, you know, we put combination of all of this together in essence. So that is a simple definition of a mathematical model. And we have a lot of applications, whether it's dealing with the population or demand for a product or speed of a falling object and so on. So there are a lot of applications in the real world, okay? And the purpose was explained in the previous page. Again, we are repeating. The previous page had the synopsis of what we had in mind. And so the process is that you start with a real world problem, you try to formulate a mathematical model, and then you try to solve uh, through the process of mathematical calculation, okay? And you do the interpretation for your readers, for example, for those who are following that. And of course, um, it gives you a chance to predict uh, real world situations. A simple example of that would be if we make up a model for the population, and then we can go through the process, make up the model, and then we can predict the population, let's say in 10 years or 20 years, and so on. All right. So a linear function, there's nothing brand new here. Y equals f of x equals mx plus b. Everybody remembers that. The thing that I want to add here, okay, just to refresh everyone's memory about that, and then I need to, I guess, erase that. With a linear function, here's what we need to remember, okay? Slope, delta y over delta x. Change in y over change in x, which is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. There's nothing brand new here. Okay, you've seen that. So change in y over change in x, this is also known as the average rate of change of y with respect to x. And that's really what calculus is all about. We go from the average to instantaneous rate of change in calculus. In other words, it's dynamic. With that being the case, what else do we remember about linear functions? Ax plus by equals c. This is a standard form. Y minus y1 is m times x minus x sub 1. So those are the things we remember. If you have a vertical line, VL short for vertical line, x equals a constant such as a, and the slope is undefined, UD short for undefined. If you have a horizontal line, y equals a constant, and the slope is 0. Two lines are considered parallel if they have equal slopes. And different y-intercepts. Two lines are considered perpendicular, meaning they make a 90-degree angle at the point of intersection if their product, the product of their slopes is -1. This is one way to write it. Or one may write m sub 2 is -1 over m sub 2. All of this we've seen, there shouldn't be anything new here. I just wanted to refresh your memory about some basics about linear models, linear equations, and so let's move on. With that being the case, f of x is given as 3x minus 2, and a table of sample values are given at top here. And obviously we can graph it. By the way, if you are looking at a case like this, I expect you to be able to come up with intercepts. Intercepts means, okay, if you're looking at y-intercept, you set x equal to 0. And if you're looking at x-intercept, you set y equal to 0. So it's very straightforward. If you are setting x equal to 0, you get -2, for example, so you get 0, -2. So for the y-intercept, it is clear that we can get replace x with 0, y becomes -2. Now, if I want the x-intercept, remember what we are going to do. Y is 0. So that means f of x is 0. That means 3x minus 2 is 0. That means x is 2/3. I'm assuming this is just all clear and bold. So this is the graph. I don't think anybody has any problem graphing. Just pick up a couple of pairs and you're done. as x increases by 0.1, f of x increases by 0.3. That's what the table shows. The simple reasoning is because the slope is a positive 3. So whatever x amount is, the y amount is 3 times that. That's why the change is concerned. So m is 3. It can be interpreted as the rate of change of y with respect to x. So that is really important for everybody to follow. The way we define the slope. Okay. All right. Could somebody be kind enough to read this example for us? Example 2, please. Go ahead, class.
I can read it, Professor.
Please.
Example 2, build linear models from verbal descriptions. A, as dry air moves upward, it expands and it cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of height in kilometers, assuming that a linear model is appropriate. B, draw the graph of the function. What does the slope represent? C, what is the temperature at a height of 2.5 kilometers?
Thank you so much, Zainab. So this is an example of a mathematical model, in which case we need to know the pairs that we are interested in. The way it's given, it's important to know which one is the dependent and which one is the independent variable. So the way this it's set up, okay, H and T, okay. So the temperature is a function of height. The way it's given could be the other way around, okay. So whatever that they give us. So with that being the case, remember what we have. We have two pairs. If we could write this, pretty much we're done. So I highly recommend for a case like that, write your pair symbolically, because normally we go with x and y, or maybe x and f of x, okay. Because we are using different variables, we don't want to get confused. So let's start with the pair. So change your x and y accordingly, in this case, h and t. So the ground temperature, that means the height is 0, is 20 degrees, okay? And then 1 kilometer is 10 degrees. So it's in kilometers, okay? And remember, 1 kilometer is 1,000 meters. Kilo means 1,000. So you need to find the slope. The slope is what? Rise over run. Change in y over change in x. However, the y is being replaced by t, or temperature, and the x is being replaced by h, or height. So I recommend you write the formula that you know, okay, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and then adjust it accordingly for yourself. So when you go back to the same question, even 10 years down the road, you know why you wrote the formula. So you're using the slope formula, okay? And so plug in, you come up with -10. In the previous page, I gave you the formula y minus y1, okay? Let me just write it up here, maybe with a different color. Let me see if I can grab a different color here. This one, okay. So y minus y1 equals m times x minus x sub 1. Now class, we are going to use the variables that we have here, okay? So you can use this formula, and I'm going to go with both formula. Y minus y1, so we are going to use t minus t1 equals m times x minus x sub 1, h minus h1. And you can come up with the answer. However, if you look at this question, you notice that one of the pairs is the y-intercept, okay? Or in this case, the t-intercept 0, comma 20. So let me make sure we understand what I'm referring to. Look at this pair. Therefore, instead of using the point slope, you can take the easy way out. Y equals mx plus b. Let me write it up here. Instead of that, you can write y equals mx plus b, in which case becomes t equals mh plus b. That would be an easy way out. And you write the formula. T becomes negative 10h plus 20. Again, normally you have to use the point slope. In this case, you don't have to. Of course, anytime you are dealing with a linear function, ultimately you have to put it in a slope-intercept form in calculus, unless otherwise mentioned. Always y equals mx plus. So that's the case, and you can easily graph this. You have a couple of pairs given to you, and you can make up more. What really is important in a case like this, you're looking at the height, the way it's set up here, we don't want to go negative, and so that's why on the left side of your vertical axis, you don't have anything, okay? And finally, what is the temperature? At a specific height, then you replace it accordingly, and you calculate it, okay? So first, the definition of a slope. When the slope is negative 10, what does it mean? That means the slope is negative 10 degrees Celsius per kilometer, okay? So as we go up, for every kilometer that we go up, we lose 10 degrees. That's the bottom line, okay? So it gets colder by that much, by 10 degrees. And of course, 2.5 kilometers, you replace it, you come up with the answer. Okay, so that's very straightforward. All right, so again, to recap this question, when you read a question like that, it is important to understand what's given first and foremost. So we write the given symbolically, and then it becomes fairly easy to deal with, okay? All right, let's go to more functions, okay, that we have seen as essential functions there in pre-calculus. Polynomials, everybody remembers the definition. The only thing I want to add to this, a sub n all the way to a sub 0, those are coefficients, and they can be any number. N minus 1 all the way to 0, if you will, those are the power or the degree or the exponent, and they can only be whole numbers. Can they be 0? Yes. But they have to be positive numbers aside from 0, and they have to be whole numbers, okay? Not integers, whole numbers, because integers can be also negative. So that is the restriction that I'd like you to remember. The domain in all of them is all real numbers. There is no whole, there is no vertical asymptote, there is no discontinuity when you graph, and the degree is n. If we put them in descending order, the first term gives us a lot of information, and also the idea known as the end behavior, because when x becomes large, the first term takes over, known as the leading term. So this is called the leading term. It's in descending order. And a degree is n. So just as an example, you have already this, seen the linear function, degree is 1, and quadratic function ax squared plus bx plus c, it's 2, and so forth. So there is really not much here. It's a good old stuff you've seen. So Here's an example of a polynomial function, and it is put already in descending order. So it's very easy to see that in this case, the leading term is 2x to the power of 6. And the degree is therefore 6. Okay, class? The leading term is the first one. Here's the leading term. Leading term. I can't emphasize this enough. And why is this important? Because it does have an effect on the graph of the functions. So, everybody remembers the quadratic functions. The general idea behind that, if you look at the leading term again, ax squared, depending upon the value of a, if a is positive, the graph shows that it opens up, and if it's negative, it opens down. So in this case, for example, a equals 1, which is positive, okay? And in this case, a is negative, which is negative, and it opens down. Now, it so happened that all functions, okay, all polynomial functions with an even degree, they pretty much follow ax squared. In other words, if x is to the power of 2 or 4 or 4,000, as long as it's even, it follows the same concept. That's the idea behind the leading term. It opens up if a is positive and down if it's negative. One way to look at this concept is that this is known as the end behavior, meaning what happens as x goes to infinity. I really hope everybody is following the concept, meaning what happens when x goes to infinity. If you look at the first graph, you see that y goes to infinity, okay? But, and if x, in fact, if x goes to plus minus infinity, y goes to positive infinity. Whereas in this second case, as x, okay, goes to plus minus, and this is known as an end behavior. Y goes to negative infinity, meaning in the first case, it goes up. So we are dealing with the end behavior in the first and second quadrant. And in part B, the third and fourth quadrant, okay. Cubic functions, okay, and anything that has a degree even follow that. So in the case of a cubic function, ax cubed plus bx squared plus cx plus d and continues. And that's it. And so it follows, again, the leading term class, okay. The leading term is important, the way the graph looks like, okay. So I hope everybody's clear on that. So let me just give you the basic graph of y equals x cubed by using a different color here. So if I have this function, so roughly this is the graph of y equals x cubed. So as you can see, the end behavior gives us the first and the third quadrant, which means when the degree is odd, okay, degree is odd, 3 or any other number that is odd. The end behavior is like y equals x cubed if a is positive, and it's like y equals negative x cubed if a is positive. So when a is positive, this is the end behavior. Now, what is the end behavior for this cubed function? X goes to infinity, y goes to infinity. x goes to negative infinity, y goes to negative infinity. So this is the case here. I want to quickly show you. So as you can see, for example, look at this one. This looks like it. So the first case, I'm going to call it number 1. And look at this last one. I'm going to call it number 3. Okay, look at the end behavior. For number 3, the exponent is the leading term. You're looking at the leading term, 3x to the power of 5. The degree is 5, is an odd number, and it has the same end behavior. On the other hand, if you look at part B, let's look at part B, everybody. Look at part B. What do you notice here? X to the power of 4. So it is just like y equals ax squared, because the leading term has a leading coefficient 1, which is positive. Okay. So I hope everybody is clear on that. The thing I want to quickly add, I want to show you the graph of y equals minus x cubed. So if we happen to have okay, this is probably the worst graph you've ever seen in class. I know that, but what can I tell you? Y equals minus x cubed. Now, if you look at the end behavior, okay, the second and the fourth quadrant. So if the leading term has a leading coefficient which is negative, that's how it works. And I hope it's coming back to all of us. Okay, we remember that from before, right, class? So with that being the case, let's look at more stuff. Okay. So the power function, okay, y equals x, x squared, x cubed. Just add to the exponent and see how it looks like. Just right here, you notice that, for example, x cubed and x to the power of 5, they look almost the same. X squared and x to the power of 4, they look almost the same. It does get flatter at the origin in both cases when the degree becomes larger. And again, if you want to graph it with details, we've got to pay attention to that. But I'm basically talking about the end behavior. In fact, look at y equals x. The degree is odd, 1, and it has the same behavior as y equals x. So that's what I want you to remember. So when n is even, the graph is similar to y equals x squared. When it's odd, it's similar to x cubed. And as n gets larger, okay, y equals x to the power of n becomes flatter near 0. Okay, so those are the observations we can have by looking at these graphs and see what happens when we add to their exponent. Okay, so that's it. General shape, I hope it's straightforward. Okay. Continuing on the thoughts, there's a lot of stuff here that we've seen in pre-calculus. Remember, we teach this over the course of maybe, a couple of chapters in pre-calculus. So we're going through this fairly fast. If you need, you can come back to this, or you can even pick up a pre-calculus text and study that. Okay, power functions, root functions. When we look at the exponents for x, okay, we've looked at the power functions previously. If we make it into a fraction, it really becomes a root function. For example, when we say f of x is x to the power of 1/2, that means the square root of x. Okay, that's the idea. So x to the power of 1 over n. Remember, n is being replaced by 2, so it becomes square root of x. Okay. The domain, many times the graph is helpful, and these are some basic elementary functions that we are supposed to know the graph, okay? And so if you look at this, and by the way, another way of looking at it is the upper half of a parabola x equals y squared. Everybody remembers x equals y squared is a parabola that opens sideways, and because the coefficient for y squared is positive, it opens to the right. If it's negative, it opens to the left. This is what we did when we discussed conic sections, if you remember in previous courses. So when the index n is called the index, okay? Index is odd, square root of x or square root of, or the fourth root of x or the sixth root of, they look similar. Of course, the larger the index, the closer the graph is to the x-axis, the shorter the graph in essence. But essentially they look the same and they have the same domain. And the same thing happens if it happened to be, the index happened to be odd. They look like a y or f of x equals cube root of x, and as you notice, in this case, the cube root, the domain is all real numbers, and it's really not a problem. I hope everybody's comfortable with the concept. Okay. So with that being the case, I think we are ready to move on. Again, refreshing your memory about some of these essential functions. Reciprocal function, one of the functions that we have graphed in previous courses, there were rational functions, but specifically a basic one, y equals 1 over x. You can think of it as x to the power of -1. And as far as the name and terminology is, by the way, it's a hyperbole, okay? But in any event, you can see the graph y equals 1 over x. There are applications in physics and chemistry. I'm not going to go over that, but I just want to make a point that there is a reason we learn it. There are applications of just about everything we study. So remember, in the case of y equals 1 over x, how you graph it. Vertical asymptote, the denominator is 0, so x equals 0. And horizontal asymptote, you actually need to take a limit and let x go to infinity or negative infinity. But the easy way out that we did it in pre-calculus, we looked at the degree of the numerator versus the denominator, and we made a decision because the degree of the top is less than the bottom. The top has a degree 0. The bottom has a degree 1, then y equals 0 becomes our horizontal asymptote. Rational function is generally defined as p of x over q of x. Just to refresh your memory about rational numbers, if you recall, rational numbers had a specific definition. It is ratio of two integers, meaning anything that you can put in the form of a fraction where the top and the bottom are both integers is considered a rational number. That is how you prove a number is a rational number. And so that is the restriction. For rational functions, the top and the bottom are both polynomials. You can, of course, 1 over x, you can see the graph, the domain, all of the above, and we will have a discussion as far as, these functions later on with more details when we look at graphing and see how they are basically done from A to Z, okay? But for now, and again, you have seen this before, there's really not much to that, but just in case. Now in this example, as far as the graph, I don't expect you for a graph like this to necessarily do it by hand, although it can be done by hand, and we'll see it in later chapters. We have done this in previous courses, such as college algebra and pre-calculus. So you should be able to do it by hand. Needless to say, it takes a long time. I don't expect you to do something like that by hand. One of the things that I expect you to see is that what is the domain? Set the denominator equal to 0 and exclude it. So plus minus 2 is out. And if we were to rewrite it in an interval notation, I'm just reminding you how the interval notation works. It's important that we know that class. I hope everybody remembers that. Okay. So that's the only reason, I wanted to put up that format as well. So having said that, again, we are going to move on. A lot more functions coming up. Uh, Algebraic functions. So we have learned all of those functions so far that are essential functions previously, but what happens if we mix and match? Okay, for example, something like f of x equals square root of x squared plus 1, or if you look at g of x, the numerator is a polynomial function, the denominator is not, or the next portion of it. These are called algebraic functions, okay, algebraic functions as far as the terminology goes. And again, the graphs are really complicated. It's not that it cannot be done, but it takes a long time to do it. And there are examples that, again, we use in the real world. For example, the theory of relativity, that m or f of v equals m sub 0 over the square root of 1 minus v squared over c squared. Everybody has seen E equals mc squared, but this is the formula that is about the change in mass. As you probably remember in physics, mass is constant because we cannot travel near the speed of light. Speed of light is 300,000 kilometers per second, okay, or 3 times 10 to the power of 8 meters per second. All right, other functions that are important to discuss are trigonometric functions. I expect you to remember the basics. You don't have to remember everything about it, but just the basics that we know how to craft a rough sketch, for example, for the sine and the cosine function. So take a look at the sine function. What I'd like you to remember, a complete cycle is this portion. And for a basic function, we go from 0 to 2 pi, okay? And 2 pi is the period of the function. And then you continue indefinitely on both sides. The domain is all real numbers. The range goes from -1 to 1. So we need to know that. If you look at cosine, here's the basic function, again from 0 to 2 pi. And domain is the same thing. By the way, sine and cosine are just the same functions. They have been shifted by pi over 2, okay? So the period is 2 pi. And with that being the case, as a periodic function, if we add 2 pi or multiples of 2 pi, we get to the same function. When it comes to tangent, okay, tangent is sine over cosine, so wherever cosine is 0, okay, we end up with what's called a vertical asymptote. For tangent, here's your basic graph. One complete cycle. And it looks almost like y equals, x cubed, and you have a vertical asymptotes, okay? Cosine is 0, okay? Cosine is 0. You get the vertical asymptotes. N plus 1 times pi over 2. Cosine x becomes 0 at all multiples of pi over 2. I hope you remember that. And so the domain has a restriction, but the range doesn't. As far as cosecant, secant, and cotangent, if you recall, all of them are the reciprocals, right? Cosecant is the reciprocal of sine, secant of cosine, and cotangent is one of the tangent. You just flip them over, the graph should be fairly straightforward. that shouldn't be any problem. So those are trigonometric functions, and just also a quick, I think I want to use a different color here. Okay, so remember t is 2 pi, okay, t is 2 pi here, and t is pi here, the period, okay? That's why when you want to graph it, you want to pay attention to that. And the other thing for the sine and cosine, you probably remember that we cut it into 4 arcs. This is 1, that one is second. Let me use a different color. This is the third one, and yet another one. This is just to refresh your memory about graphing. So there are 4 arcs. 1 and 2 and 3 and 4. The idea was that find the period, cut it into 4 pieces, and you have your 4 arcs, and then when you have that graph, then continue indefinitely on both sides, and that becomes the graph of interest. Very straightforward class. All right, let's move on. This thing, we have a lot to do, class. So those are some functions that we've seen. I hope everybody remembers what's going on here now. The next thing, which is a big deal, exponential and logarithmic functions. They are inverse functions, and as you remember, inverse functions, they have graphs that are symmetric with respect to the line y equals x. So as an example, y equals a to the power of x versus y equals log x base a. The only thing I want to make a point of in this case and in that case, a is larger than 1. A is larger than 1 because, first of all, it can't be 0, and then, I'm sorry, it can't be 1, my apologies. And if it's between 0 and 1, the graph looks different, okay? It flips over. So we don't want to, you know, mix them up. In other words, this would be the graph of y equals a to the power of x. If a is what? Between 0 and 1, for example, 0.1, okay? And then you use a different color. This would be the graph of y equals log x base a. Again, a is between 0 and 1. So you want to pay attention to that. More importantly, here's the definition of a log. If you remember the definition of a log, you will have absolutely no problem with any of the properties we're going to discuss in the next page that you are supposed to know, and you are supposed to know it really well for the sake of the course. Okay, there's a portion later on we look at known as logarithmic differentiation. So y equals log x base a, x is a to the power of y. In other words, what is log? Log, simply put, represents the exponent class, okay? So if I want to go with the following question, let me see where I have them. If I'm going to say, okay, 2 what power is 8? It is the same as saying log 8 when the base is 2 is equal to that. They have the same meaning. So if we know the first one, we should know the next one. So there are a lot of properties here, okay, that I expect you to know. You really need to remember these properties, class. First of all, we have proved all of them. Some of them are very straightforward. Just look at this, you know, arrow that I show you. A to the power of 0 is 1. A to the power of 1 is a. The next one is the product rule, then the quotient rule, the power rule, and these two, the last ones together refer to the fact that log and exponential functions are inverse of each other, okay? Now, I'm gonna show you the same thing for common log and for natural log. What I'd like you to do at home is that, see if you can produce that on your own, okay? You have the answers here, but you really need to practice. I know in the past, students have had quite a bit of problem with logs. So here's the common log. So all you have to do, change the base to 10. When you change the base to 10, when you want to write the log, you don't write the base A. That's all, class. So take a look. In all cases, the base A is gone. Okay. So the only thing that you want to be careful of is really this last two, being able to make them up. Okay. And I hope you see how they look like. Natural log, y equals ln x. So we don't write log anymore, we write ln, and it becomes a natural log. So x is e to the power of y. And look at the properties. Instead of log, just write ln. And again, these two are the ones that sometimes students have a problem with. You want to make sure that you can handle that, class. I really can't emphasize this enough. So here's your, you can think of it essentially, here's your homework. The first one, I'm assuming you have it, okay? I highly recommend that you go from the first one to the second column and to the third column on your own. See if you can make it up in no time. Until you become comfortable with that, you need to practice, okay? So when we get to logarithmic differentiation, you will have an easy time. All right, classify the following functions. Those are very straightforward, class. I don't want to spend too much time on those. I think we know what they are, but just for the sake of argument, okay? Let's quickly discuss it. The first one is something to the power of x. It's some number, 5. It doesn't matter what number. So that's an exponential function. Part B, x is to some power, 5, 500, 2.1. Even if we had x to the power of e, it's the same thing. It's a power function, or you can say it's even a polynomial function. Part H, it is not a rational function because of the square root of x, okay? And the last one is a polynomial function. So part C is not a polynomial because of this one. If we had it as x, there it is a rational function. Instead, it's simply put an algebraic function. Let's quickly look at one more example for this section, class. Could somebody be kind enough to read this question for us, please? Class? Could somebody read this question, please?
Yeah, I can.
Perfect.
Monthly cost of driving a car depends on the number of miles driven. April. Cost 380, miles driven 480 miles. May. Cost $460, miles driven 800 miles. Do you want me to read the options too?
That's fine. I appreciate that, Stevens. I appreciate that. Thank you so much. So we want to solve this linear problem. Again, it's important to see what's given. I'm going to go through this with you. The very first thing is that understand April and May are giving us the following two pairs. Notice what we are going to write. Before we write the pairs, normally we write x comma y. Because we don't want to have any confusions, we start with what we should write because the letters are changed from x and y to what? Distance, which is in miles, cost, which is in dollar, D and C. Okay, so therefore, according to this, remember it says, part A says express cost as a function of distance D. So distance is the independent variable, is like x. And cost is the dependent variable, just like y. In fact, if it helps, you can even write this underneath. D is like x and C is like y. And then you can even write the, go from A to Z with x and y. Okay, here's one idea. Go with x and y, finish the job, come back. Anywhere you see x, change it to D. Anywhere you see y, change it to C. The reason I mentioned that, I've seen in the past, sometimes students have a difficulty with that. So under D, I'm writing x. Under C, I'm writing y. Deal with x and y, come back and change it, okay? That's one way to do that. So the very first thing is to find the slope. The definition, again, go with the y and change it to the new variables. And you go through the process, it becomes 1/4. Now, none of these pairs are y-intercept, or in this case, the cost intercept. So you have to go with the point slope. Everybody remembers the formula for the point slope. Y minus y1 equals m times x minus x sub 1. So C minus C sub 1 is 1/4 D minus D sub 1. You go through the process and you have your cost function, okay? Now, what is the cost when we do 1,500 miles? Okay, we replace that with 1,500 and we come up with the cost. Okay, if we drive it for 1,500 miles, okay. Graphing shouldn't be a problem. Again, we don't go on the negative side, okay. It's X and Y, okay, or D and C. So class, so X is the same as D and Y is the same as C. In fact, those are the axis, the D axis and the C axis. I want you to know that, but so you can distinguish between the two. The slope is 1/4, okay? So 1/4 of dollar represents the amount of increase in cost for every mile driven. So for every mile, the cost goes up by 1/4. So if we go 4 miles, it goes up by $1. The C intercept, or the Y intercept, okay, represents the fixed cost of operations, okay. You're driving the car, there are some fixed costs involved. It could be the insurance, it could be the lease, or whatever the case might be, okay. And of course, it is explaining why a fixed monthly cost such as insurance and car payment, as well as costs that increase as you drive, such as gas and tires and etc. That's why it makes it a reasonable deal to have a linear function representing the cost.